Assalamualaikum and hi, my name is Amalia Arika Bintrudi and my metric number is AE190076. So now I will talk about the introduction in this project. So based on the requirement loading provided, we analyze and redesign the industrial electrical system to make the network more sustainable. So based on the provided industrial loading, this project estimate the size of the incoming transformer, so the 5 distribution transformer, each with the different induction motor, and the project approach illustrate the industrial network design of the distribution in this undertaking. So for the industrial installation, a one-line diagram and distribution transformer T1 until to T5 were built, and then utilizing the diversity factor and utilization factor calculated by the Microsoft Excel. And this project also estimate the load for each division. For the sizing of the transformer is decided by the calculation that compile to the standard. Next, the technical problem. There are numerous technical issues that may arise before, during, or after a project in the industrial field. So a transformer is a tool used to increase or decrease electrical voltage. Transformer also play a crucial role in electrical system, and it's obvious that mistakes happen frequently everywhere. So we shall explore various transformer failure in this project. So in this project, we face the technological challenge like the necessity to examine system effect and regulated sustainability criteria. So the next technological challenge is not to plan a low carbon system while achieving the desired result. And then other than that, the transformer has a lot of technical problems, such as transformer fail to be worked due to many factors, and the current of the TR is also fault for the overloading or overheating fault. So the load should be reduced if necessary to match the rate current of the TR. Last but not least, the transformer's temperature was rising since the oil level was low. And then the project objective: first, specify the industrial loading and estimate the incoming transformer sizing. Next, to estimate the industrial power system while taking the industrial loading, energy resilience into account. And then lastly, design the industrial electrical system taking sustainability and the environment into consideration. Next, the project methodology. This is figure 2.1, which is the plot diagram of the overview. The project planning: first, we complete the group formation, and then we distribute a task, and then we start to sketch a one-line diagram for given industrial load. Next, complete the transformer sizing calculation, complete the cable sizing calculation, and also we are complete to redesign work of existing industrial network and complete the report.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Anafika binti Omar. So I will be explaining to you about our single line diagram. So the first one, you can see our transformer from 33 kV, which will be step down and goes to the T2, 11 kV. And then from there, it will also be step down into 3.3 kV to supply load to 3 motors. And then for T3, the transformer will step down to 0.415 volt to supply load to 2 lamp loads. And for T4, the transformer will step down to 0.415 volt also to supply load to the synchronous load. And lastly is the T5, which is to step down the 3 kV into 0.415 volt also, so that it can supply load to 1 motor and 2 MCC. So for the next part, which is where the 60% increment of load, so we have to add another 2 transformer, which is T7 and T9. And for T7, we also need to step down into 415 to supply load to a motor. And lastly, T9, we also need to step down to 415 volt to supply load to supply power to 2 loads. That is all from me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amir Hamidun, AE190056. So today I'm going to explain about the estimation and transformer sizing that our group already calculated in Excel. So first thing, we must know our motor rating for each load. So to find this motor rating, we can use the given specification at the assignment question, such as the efficiency, power factor, and the horsepower. So after we get the motor rating for each load given, we must need to know our motor input power in kilowatt. So to find this motor input power, we must divide our motor rating with the efficiency, and same goes to all the load given. But for alarm load and lighting, there's no motor rating, so we assume as 0. And after we get the motor input power, the another important thing is to find the apparent power. So to find the apparent power, we must divide the motor rating that we already calculated, divide with the K factor. So after we got all the apparent power for each load, we sum it up and we got this value. And same goes to motor input power. We must get the total of the motor input power. So the next step is we must calculate the apparent power using the diversity and utilization factor. So here Ku is the utilization factor and the Ks is the diversity factor. So to find the apparent power of utilization factor, we must multiply it with apparent power that we get before this. We divide it with the utilization factor 0.80, and we get the value of the apparent power, the new apparent power. And then the diversity factor also, we must get the value that we already multiply with the utilization factor. We multiply with the diversity factor 0.80, and we got the new apparent power. We proceed to the transformer sizing. After we get the apparent power demand value, we must to calculate the transformer size, which is the total load 65% of the transformer. So it means we must divide the apparent power demand value with the 0.65 for all the transformer. After that, after we got the value, we must choose our transformer size by using the rating given in the slide. So after we analyze the value, we can choose the transformer size, and this MD we also we analyze the criteria and choose the MD. So for this transformer secondary, we use the typical rating that given in also in lecture slide. So we assume the transformer secondary 11,000 for T1, T2 is 3,300, T3 is 415, T4 is 6,700, and T5 is 415. So dependent, we also choose from the rating given. So for transformer 1 until 3, we choose 5%, and for transformer 4 and 5, we choose 7%. So the function of the table is to know the transformer rated current and transformer short circuit current to be used in the table sizing. So to calculate the transformer load current, we must get the transformer size, this value. We divide by square root 3 and multiply with the secondary value, and we divide with 1,000. We multiply with 1,000, and we got the transformer load current. Same goes to transformers 2, 3, 4, and 5. After that, we must find the transformer short circuit current. So the transformer short circuit current is the value of transformer load current we get here is divide with impedance, and impedance is divide with 100. So we got the transformer short circuit current. And for the transformer apparent power, we must square using this formula, square root 3, multiply with the secondary, multiply with 1,000, and multiply with transformer short circuit current, and divide by 10,000. So after we get the value, we must do to fulfill the criteria. We must also calculate for the motor details. So for the motor detail, the voltage drop must be not uh, more than 10%, which is must be less than 10%. So motor full load is below 65% of transformer full load.
So this is the our task to add on two division for the total load increment 66% from our existing load. So this is our calculation. This is existing load that we get 5,735, and this is a 60 total increment for our total existing load for 3,441. So this is our calculation. So we divide by 3 to get for one. So we add on the motor, 3 motor for 2 division, and so this is our calculation for 60%. For one total motor we can get 1,000, but we just use 500 total rating and we get 668.27 for apparent power. So for 2 division we just use one transformer for 2 division and 3 motor. So this is our transformer selection rating, and this is for our transformer detail. And so the transformer rating selection for the final transformer size is 60,000 kVA, and number of motor starting power is 3, and the final transformer size is 2000 kVA.
Assalamualaikum warahmatullahi taala wabarakatuh. I'm Muhammad Alif Nazmi bin Asmadi, and I will explain about the cable sizing for transformer and motor. So the type of cable that we choose is copper, insulation XLPE EPR. The final temperature is 250 and the initial is 90. The core is multi-core. And next we should go to the cable sizing. So the cable sizing for transformer 1, which is the primary, we get the I short circuit current is 10497.86. So the cable sizing calculation uh, the formula is square root I short circuit current squared times T over with K. So 73.41, so we choose 95 mm. Next one is for transformer 2. The short circuit current is 22044.28, and the A we get is 154.16. So we choose the cable size is 185 mm. The red one is transformer. The black one is for the motor cable. So this one is for the motor. We get a short circuit current 1461.80, and the A is 10.22. So the cable that we choose is 16. For motor 2, we get 3221.40 for the ISC, and the A is 22.53, and we choose 25 mm squared cable. Next one is motor. We get ISC is 4574.40. The A is 31.99, so we choose 35 mm squared. For transformer 3, we get the IC is 27824.11. The A is 194.57, so we choose size of 240. Next, motor we get 12841.90 for the IC, and the A is 98.80, so we choose 95 mm. Next, we get 642.09. The A we get 4.49, so we choose the size is 6. For transformer 4, we get the IC for transformer is 6248.38. The A we get 43.69, so we choose 50. Next, the IC is 1870.15. The A we get is 13.08, so we choose 16. For the last transformer, which is transformers 5, we get the IC is 39748.73. The A 277.96. So the size of the cable that we choose is 300. For the load, uh, as you can see, is 61559.40. We get the A is 43.07, so we choose 50. The IC we get is 11083.63. The A we get is 77.41, so we choose 95 for the cable size. Last one is 5655.79 for the IC, and the A is we get 39.55, so we choose 50 mm squared. This is for the cable sizing before the increment, the additional of 65% of load. So we go to the increment. The type of cable that we choose is same, just copper, XLPE, PR. Basically it's all the same, the same size. For transformer 6, we don't choose any size of cable, because this is for the calculation of load estimation and transformer sizing only. So we can say that the cable choose for the cable sizing too, same with the cable sizing, the additional just for the transformer 6. So for transformer 1, we choose 95 mm squared. Transformer 2, 185 mm. Transformer 3, 240. Transformer 4, we choose 50 mm. And the last one is we choose 240. These are for the load, and these are for the transformer. So basically, we choose cable sizing higher higher than the A that we get from the cable sizing calculation. For the IC, we get the iMotor from the transformer sizing, which is like this. 73.09 is the iMotor for the motor 1 in transformer 2, and follow up by the other motor. So I think that's all from me for cable sizing calculation in mm squared.
Assalamualaikum, my name is Eli Adila binti Ansarudin. I will explain for the project outcomes and discussion. So for the 3.1, which is outcome of load demand estimation, for estimate load demand, we choose small factories as an installation area section. So for the calculation of the estimated load demand, we use Microsoft Excel as shown in Appendix A. And then for the total apparent power, we get 5,735.15 kVA. Okay, for the apparent power demand, we also use Microsoft Excel, and for the utilization factor, which is KU, and diversity factor, which is KS, we are considered for each load and division, and select appropriate value for the utilization factor. First, we need to determine the type of load being used. Because the induction motor and synchronous motor won't function at 100% their apparent power, but neither they will work at 50%. So we choose 0.5 as the utilization factor for every load. And then for the other than lamp load meter, heating, lighting, and MCC, we choose option 1 because it can run virtually entirely, which is 100%. In this load demand, we have 3 stages, which is KS1, KS2, and KS3. Which is KS1 is the industrial load, smaller voltage, and by using function circuit table, we assume that KS1 is equal to 1 because the motor are under more than 100 kW of load. And then we also need a same assumption for lamp, heating, and lighting, which is equal to 1. Then by using the table of distribution switchboard weighted diversity factor, we assume that division 1 and division 2 have values which is 0.9 for lamp load, heating, and lighting. Okay, so for division 3, which is have a small variance in that, we assume 1 MCC1, MCC2, and also induction motor for the synchronous motor. So at the end, we obtain the primary general value distribution board, which is 4447.45 kVA. Okay. And then for 3.2, which is outcome of industrial network design, which is for the single line diagram in figure 3.2. A single transformer connected by a single cable serves as the transformer for incoming power supply from TMB. Based on the size of the transformer and load in the circuit, calculation must be made for the 10 buses and 9 cables that were chosen. Every primary transformer has a circuit breaker and a fuse that installed as a safety measure to guard against overcurrent or short circuit. For figure 3.1 is our single line diagram. And then for the 3.3, which is result and discussion on transformer and cable sizing, which is for criteria 1, each transformer rating is established in accordance with the competition present in table 3.2, which is here. So in the table 3.2, we have 5 transformer type, which is transformer 1 until transformer 5. And for the value of apparent power demand is stated at here. And also for the rated apparent power after 65% in kVA. And also we have the transformer rating selection for every transformer. To meet the criteria 2, voltage losses brought on by the massive motor starting at the transformer must be less than 10%. And for the table 3.3, it shows the predicted voltage losses caused by the largest motor starting for each transformer. And then for the table 3.4, it's display calculation for each motor in facility. And then the choice of transformer rating is strongly suggested by the requirement for a lower or 10% voltage drop at the transformer in table 3.2, which is it has a voltage drop, and we get that all the transformer have a same voltage drop, which is 10. Next, for 3.4, which is environment and sustainability, which is our proposed solution. So we propose that advanced lighting control can reduce energy consumption by incorporation motion sensor that ensure the right areas at lit without having to keep the lights on around the clock, such as division 2 lighting can be used with Energy Star certified LED bulbs. And then because it's consumed 90% less energy while still producing the same amount of light as the incandescent bulb. And then it also can implementation of smart HVAC controls that can help manage and reduce energy usage by limiting consumption in empty parts of a building and also optimizing usage during time of high demand.
Conclusion, there are lots of things that we need to understand and learn to make sure that the project will be done perfectly. For example, understanding about the single line diagram in industrial for installation and how to create the single line diagram. Next, the information of the development of high voltage test transformer. Our plan and use high voltage testing framework give the arrangement of the most change transformer in regard boundaries and cost. The high voltage of testing a transformer are the fundamental of security, high productivity, lower cost of development, and saving of energy. The transformer is exceptionally reliable gadget and it can offer for quite a while if keep up with overhaul generally. Microsoft succeed can assist understudy with finishing the power utilization and the general power element of the modem established computation, and it's extremely used for understudy and to modem of power framework that can be utilized by service organization. So the weakness of this design is the purpose plan enjoy on benefit and inconvenience will examine and change. This plan need to really costing contrast with other plan in light of how much link used or others. The plan need working on productivity of transformer in view of complete working burden. The transformer need work somewhere in the range of 80% or 100% to full burden rating. Finally, the effectiveness through the size. Bigger center material will expand how much copper utilized in the creation cycle, and the transformer are conveyed in huge size. That's all. Thank you.